So our first example is me jumping out of a plane with a parachute on my back. I have a mass of 55 kilograms. And in this example, we're not ignoring air resistance. So we're saying the air resistance increases, obviously, when I pull the parachute string. So before I pull the parachute string, the force of air resistance is 50 newtons on me. And then afterwards, we would say in part B, it increases to 539. So before we can answer this question, we have to draw all the forces acting on, we have to basically draw a free body diagram. So there I am falling from the plane, and what are the forces acting on me? Well, we have, now something you can never forget, even though it doesn't talk about it in the question, is the force of gravity, and it's acting straight down towards the center of the earth. And that's always there. Okay, and we can actually, if you go back to that forces sheet that I gave you at the beginning of the unit, there's a formula. We'll talk about that in a second. And then the force of air resistance is a thing that's sort of working against her falling. So as I'm falling through the air resistance is trying to slow me down in a sense. So you can say that the force of air resistance is acting upwards. So these are the two forces acting on me. If I choose a sign convention, I would say up is positive and down is negative, say. We can do it like that. So what I'll do now is we'll figure out, we actually want to put numbers in here. Okay, the question tells us that the force of air resistance is 50 newtons. So that's 50 newtons acting up. Now we have a formula for the force of gravity, and it is that Fg is equal to mg. This is always true for an object on the surface of the earth. The force of gravity is equal to the mass of the object times, so if, let me just put a note in here about this. This is the mass of the object in kilograms, and this is the gravitational field strength. Field strength. And it has a value on the earth of 9.8 meters per second squared. All right, so we can plug it in the numbers then, because we were given that my mass is 55 kilograms and G is 9.8 meters per second squared. You'll remember from the lab we did that a kilogram meter per second squared is a newton. So we can figure this out by going 55 times 9.8, which equals 539. So this equals 539 newtons. So on my diagram, so if I wanted to find the net force, F net, we write it like this. It's equal to the sum of the forces. And what this means, here, let me write it here. Sum of the forces. So if I look at this up and down direction, what I see is that there is a force of air resistance, which is positive, minus the force of gravity, which is negative, which is that's why I'm subtracting it. I mean, another way you could have said this is force of air plus negative force of gravity, right? That's another way to have written it. So then what we're going to do is plug in the numbers. We've got 50 newtons minus 539 newtons. So the answer here is 50 minus, that is negative 489 newtons. Oops, 489 newtons. The negative means down. So this really means 489 newtons down. So what's the net force acting on me? It's 489 newtons towards the earth, which is the answer to this question. Okay, in part A. This is all for part A. So for part B, so what happens is as you speed up, as I get faster and faster, like I'm falling through the air, I'm accelerating, I'm getting faster and faster, what doesn't change is the force of gravity acting on me. So it's still Fg, it's still mg, right? That doesn't change as you're falling. So it's still 55 kilograms divided by 9.8 meters per second squared. It's still 539 newtons. But now what we're saying, or what the problem is saying, is that after I pull the string of the parachute, the force upward increases the force of air is equal to 539 newtons. All right, so you can see that those numbers are not coincidentally identical. So what we're going to do down here is say now F net is equal to, same equation, sum of the forces, and this is equal to F air minus Fg, but in this case it's 539 newtons minus 539 newtons, which equals 0. So there's no net force acting on me as I'm falling in the second example. This is an example of something we call terminal velocity, and we'll get into this with a lot more detail in the days to come. Okay, but in the first part of the problem, when I first jump out of the airplane, I'm still accelerating, so I can even draw my acceleration. It's down, but when I get to the part where I'm coasting down with the parachute, the forces are balanced.